Hi boys and girls, this is lecture 4.5 in Unit 4, a summary of curve sketching. This is the second part of a lecture regarding this topic. You can see here on this first slide that I provided once again for your perusal the list of elements that we'll be analyzing for each graph. So let's get started. Analyze and sketch the graph of f of x equals x squared minus 2x plus 4 all over x minus 2. This is another rational function. Let's start with the y-intercept. The y-intercept is found at f of 0. So we'll put 0 in for x in the function to discover what the y-intercept is. We'll have 0 minus 2 times 0 plus 4 over 0 minus 2. This simplifies to 4 over negative 2, which reduces to negative 2. So negative 2 is our y-intercept. For the x-intercepts, we set the function equal to 0. The y value is 0, and then we solve to find out what x values make this true. So we'll have 0 equals x squared minus 2x plus 4 over x minus 2. Of course, when you have 0 equal to a fraction, you really need to only set the numerator equal to 0 in order to solve for x. And even though this is a quadratic, it does not factor. So we're going to have to use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you've memorized this, or perhaps you know a song that has similar lyrics to this. And in this problem, our a is 1, our b is negative 2, and our c is 4. So the quadratic formula for this quadratic will be negative 2 plus or minus b squared will be negative 2 quantity squared minus 4 times 1 times 4, and that's going to be all over 2 times 1. We simplify this and get 2 plus or minus. Underneath the radical now we're going to have 4 minus 16 all over 2. Now that we see that the discriminant is going to be negative, this tells us that the two solutions are imaginary. We don't really need to know what the solutions are because that wasn't our purpose in using the quadratic formula here. We were trying to find the x-intercepts, which of course are the solutions to this particular function. However, now that we know that they're imaginary, we know that there will be no x-intercepts. So that answers our question, and we don't really need to go any further in trying to find out exactly what the solutions are. Now let's look at the asymptotes. Since this is a rational function, we will probably find asymptotes. Vertical asymptotes occur where the denominator of the rational function is equal to 0. So let's set this denominator equal to 0. X minus 2 equals 0 yields x equals 2. So we'll have a vertical asymptote at 2. Horizontal asymptotes can be found by examining the degree of the numerator and the degree of the denominator of the rational function. So horizontal asymptotes in this particular case, we would have the degree of the numerator is 2. The degree of the denominator is 1. Since the degree of the numerator is greater than the degree of the denominator, there will be no horizontal asymptotes in this particular function. And now for calculus. Let's take the first derivative of this function. We will have to use the quotient rule. So we'll have the denominator times the derivative of the numerator, 2x minus 2, minus the numerator, x squared minus 2x plus 4, times the derivative of the denominator, which in this case is just 1, all over the denominator squared. Something kind of glitchy happened there with my pen. This should be a 2 minus 2x. Now let's simplify that numerator. I'm going to FOIL together these two binomial terms, and I'm going to get 2x squared minus 2x minus 4x plus 4, and then distributing the negative here gives me negative x squared plus 2x minus 4, and of course that's all over x minus 2 quantity squared. These guys are like terms. 2x squared minus x squared is 1x squared. We have negative 2x minus 4x, which is negative 6x, plus 2x, which is a 4x, a negative 4x, pardon me, a negative 4x, and then we have a positive 4 and a negative 4, which cancels, so that's our numerator, over x minus 2 quantity squared. That is our first derivative. Now we'll need to find the second derivative using the quotient rule again. So f double prime of x will now be the denominator, x minus 2 quantity squared, times the derivative of the numerator, which in this case is 2x minus 4, minus the numerator, x squared minus 4x, times the derivative of the denominator, which requires the chain rule, 2 times the quantity x minus 2 to the 1 power times the derivative of what's inside, which is 1, so that's the end of that, all over, and now we have x minus 2 quantity to the 4th power. Now let's look to see what we can factor out of our two terms. Remember, now we have two terms here. Even though they look a little bit confusing, we can take out an x minus 2 from each of these terms, and let's do that and see where we end up. We'll have x minus 2 times what's left over here is an x minus 2 and a 2x minus 4, x minus 2 and a 2x minus 4. From this term, we're left with a 2 and then an x squared minus 4x. Let's think of this as a negative 2 distributed here, giving us a negative 2x squared and then plus 8x. Hope I got that right. All over x minus 2 to the 4th power. The nice thing about this, of course, is that this x minus 2 cancels with one of these, leaving just 3 in the denominator. Now let's FOIL this out and combine like terms and see what's left in our numerator. We will have, I'll just come over here with more simplification. We're going to have 2x squared minus 4x again, plus 8, and then minus 2x squared plus 8x, and this is all over x minus 2 to the 3rd power now. The 2x squareds cancel. Negative 4 and negative 4 is negative 8x plus 8x. Those cancel as well. And so we're left with 8 over x minus 2 quantity cubed for our second derivative. Okay, now it's time to use our analysis to sketch a graph of the function. As you can see, I have brought our y-intercept over from our first bit of analysis. I've also placed the vertical asymptote at 2. Remember, there were no horizontal asymptotes and there were no x-intercepts, and so I can go ahead and plot this point. 0, negative 2. We know that the graph goes through this point because it's the y-intercept. And now let's use our first and second derivative to get test intervals for where the function's increasing and decreasing and for concavity. We'll set the first derivative equal to 0. Of course, since it's a rational function, we're going to let the numerator equal 0 to find out what values produce 0, but we're also interested in places where the function is undefined. All of those will comprise our critical numbers. So first we'll say x squared minus 4x equals 0. Factor out the x. And this gives us two critical numbers by setting the first derivative equal to 0. 0 and 4. Since the function is undefined at 2, we have to add x equals 2 as another critical number. Now let's set up test intervals based on these values. We'll go from negative infinity to 0, from 0 to 2, from 2 to 4, and also from 4 to positive infinity. I'll use negative 1, 1, 3, and 5 as test points in the first derivative. Now notice when I'm plugging numbers back into my first derivative, not sure why I made those so tiny, the denominator of the first derivative will always be positive, whatever you're putting in for x squared, a positive number. So we're just trying to quickly get the sign of the numerator so that we can determine if the entire function will be positive or negative. When I put negative 1 in for x here, I get a positive 1, negative 4 times negative 1, a positive 4. That's going to be positive over positive, which means the sign of f prime of x here is positive and the function is increasing. Now let's try 1. 1 minus 4, a negative 3 over a positive number, which means positive over negative is negative. The function is decreasing in this interval. Now let's try 3. 3 squared is 9 minus 12 is going to be a negative number over a positive number. And so in this case, we have the function, the first derivative is negative here, which means the function is decreasing on this interval. And then when we plug 5 into the first derivative, we get 25 minus 20, a positive number over a positive number, means that the function is increasing here. All right, now before we move on to the second derivative, let's look at our critical numbers and determine whether they were extrema, whether they were max or min values. Remember, they're only going to be considered extrema if the function changes from increasing to decreasing on either side of it, or from decreasing to increasing. In this case, since our function went from increasing to decreasing, that means there must be a maximum value at 0. Let's look here at 2. Notice that the function was decreasing on the left side of 2, decreasing on the right side of 2. That means this isn't an extrema. Now we already knew this because it's a vertical asymptote, but I wanted to make sure that we are examining to see what's happening on either side of 2 before we determine whether or not it's an extrema. Now let's look at 4. You can see that on the left of 4 the function is decreasing, on the right it's increasing, which means at 4 we have a minimum value. Now let's use our second derivative to determine the concavity of this function. We'll set it equal to 0. There will be no x value that yields a function value of 0 here, however, because there's no variable in the numerator. But remember, we also look to see where the second derivative is undefined, and that's happening at 2, our vertical asymptote. Remember, we have seen that the function can change from increasing to decreasing or decreasing to increasing on either side of an asymptote. It can also change concavity on either side. So these must be considered when we're setting up our intervals to test for whether a function is increasing or decreasing, or for concavity. So in this case, it's the only value that we will use. We'll go from negative infinity to 2, and then we'll look at what's happening on the other side of 2 from 2 to positive infinity. I'll use 0 here just because it's an easy number to plug in quickly, and I'll use 3. Let's go to our second derivative. Of course, the numerator is always positive since it's just an 8, so let's see what the sign of the denominator is. When I put 0 in for x, I get negative 2 cubed, which is a negative number. Positive over negative is negative. Therefore, in this interval, my function is concave down. Now, on the other side of 2, at 3, I have 3 minus 2, which is 1 cubed. Positive over positive is positive. So in this section, my function is concave up. Notice that concavity did change on either side of our critical number 2, but of course it's not a point of inflection because it's a vertical asymptote. However, if it were not a vertical asymptote, we would need to look at each critical number that's generated from the second derivative in order to determine if it's a point of inflection. Now let's go ahead and use all of this data to sketch a graph of our function. And we probably should define a couple of function values first. Our maximum value is occurring at 0. Of course, we already know what f of 0 is since it's our y-intercept, but a minimum value is occurring at 4. So let's go ahead and find out what f of 4 is. Back in the original function, that's 16 minus 8. 8 plus 4 is 12. Over 4 minus 2, 2. 12 over 2 is 6. So let's go ahead and plot that point. 4, 6, which is here. And of course, we already have the point 0, negative 2 plotted since it was our y-intercept. Now, on the left side of 0, we have a function that's increasing and concave down. And even on the right side of 0, even though it begins to decrease there, it's still concave down. So my thoughts would be, since we have an asymptote here, and it's bounded by that asymptote, that we would have something like that. Increasing to decreasing and concave down on this section. On the right side of 2, we have a concave up section that goes from decreasing to increasing. Since we're bounded by this asymptote and we have to go through this point, decreasing means we have to start up here and hit that point, and then we increase on the other side, all the while keeping our function concave up. So there's a graph or a sketch of what it might look like. Now let's look at the actual graph and compare. Not bad, boys and girls. You can see that our analysis generated something very close to what the actual graph looks like, and that's the beauty and majesty of what we do. Now let's analyze and sketch the graph of a polynomial function. F of x equals x to the fourth minus 12x cubed plus 48x squared minus 64x. We'll start with the y-intercepts. Remember that y-intercepts can be found by evaluating f of 0. So as we put 0 in for all of these x values, we'll get a function value of 0. This means, of course, that the point 0, 0 is a y-intercept as well as an x-intercept for this function. But are there other x-intercepts? We find x-intercepts by letting the function equal 0. And as I rewrite this function, I'm going to factor out the x that is common to all four terms, and that's going to leave x cubed minus 12x squared plus 48x minus 64. Now, of course, we can take the x that we factored out, set it equal to 0, and realize that 0 is one of the x-intercepts, as we already knew. But how do we get the other x-intercepts from this cubic? Traditional factoring methods will not work here. We might try grouping, but we would discover it's not going to give us the factors we need. Thus, we would need to resort to the rational root theorem. We would look at the factors of negative 64. We would look at the factors of the leading coefficient 1. We would generate a list of potential rational roots, and then using synthetic substitution, we would use trial and error until we found the roots that actually do work. We would find by this method that 4 works 3 times. It is a triple root of this function, which sounds kind of exciting. But also this does mean that our function would factor in this way. The x and then x minus 4 quantity cubed. That's just another way of rewriting the original function. Now remember, as I said, I did not factor this using traditional methods. I pretended as though we were using the rational root theorem, generating a list of potential rational roots, and then using trial and error with synthetic substitution, we found that 4 worked 3 times. But knowing what the roots are allows us to rewrite the function in a factored form. Now, since there are no vertical asymptotes or horizontal asymptotes, let's look at the first and second derivatives. The first derivative will be 4x cubed minus 36x squared plus 96x minus 64. And then the second derivative will be 12x squared minus 72x plus 96. Always nice taking derivatives of polynomial functions. And there we have it. Now we're ready to begin to use our analysis to sketch a graph of this function. Notice that I have brought the information regarding our intercepts over, and I plotted the x-intercept at 0 and at 4. And now let's set our first derivative equal to 0 to generate critical numbers from that derivative. We're going to factor out a 4 here, and that's going to leave x cubed minus 9x squared plus 24x minus 16. Now once again, we will not be able to factor this cubic using traditional methods. We would use the factors of 16 and 1, generate a list of potential rational roots, and using synthetic substitution, we would find which ones work. It turns out that we will find solutions at 1, and 4 is going to be a solution twice again. However, since we're just using this to generate the critical numbers to set up intervals, we only need to use 4 once, of course, but this will give us intervals from negative infinity to 1, from 1 to 4, and then from 4 to positive infinity. I'll use 0 as a test point, 2 as a test point, and 5 as a test point in those intervals. Now I do need to know the value of the first derivative at each of these points. If I put 0 in, I can see it's a negative number. Doesn't matter so much what the value is. We're more interested in the sign of the number. Negative means the function is decreasing there. In the interest of time, I'm not going to work out the analysis for each one, but I can tell you that f prime of 2 is a positive number, which means the function is increasing on this interval. And if I put 5 back into the function, into the first derivative, I find that once again it generates a positive value, which means the function is increasing here as well. Now, before we move on to the second derivative, let's look at our critical numbers and determine whether or not they were actual extrema. Since we did have a change from decreasing to increasing at 1, we had a minimum value occurring there. So 1 is an extreme value, it's a minimum. But notice at 4 that it went from increasing to increasing, no change in the sign of the derivative on either side. Therefore, 4 is not an extrema. It is an interesting point to consider, but it's not a max or min. Now let's look at the second derivative and set that equal to 0. We can factor out a 12, and we're going to end up with x squared minus 6x plus 8. Finally, something that can be factored using traditional methods. This factors into x minus 4 and x minus 2, which tells us we have potential points of inflection at 4 and at 2. So let's use these values to set up intervals for concavity. Negative infinity to 2, 2 to 4, and 4 to positive infinity. I'll use the test value 0 here, and I'll use the test value 3 in this interval, and I'll use the test value 5 here. Now let's plug these test points into our second derivative to determine concavity in these intervals. If I put 0 in for x here and here, I'm going to have 12 times negative times negative. Negative times negative is positive, times a positive number means it's positive here, which means we have a section that is concave up. If I put 3 in for x here and here, this is going to be positive times negative, 3 minus 4 is a negative number, times positive, which means in this interval, the second derivative is negative, which means we'll have a concave down section of the graph here. And finally, let's put 5 back into our second derivative. 12 times 5 minus 4, a positive number, times 5 minus 3, a positive number, generating a positive value for the second derivative, a concave up section of the graph here. Let's look at our potential points of inflection to see if they actually are points of inflection, starting with 2. Notice that concavity changed from positive to negative. If there's a change in concavity on either side of the value, then it actually is a point of inflection. So we do have a point of inflection at 2. What about at 4? Once again, there was a change from concave down to concave up there, so 4 is also a point of inflection. Now, before we start graphing, we should definitely find some important function values here. We should find out what the function value is at 1, the function value is at 4, and the function value is at 2. This will give us at least some touchstones when we're graphing. We have, of course, the function value at 0, which was a y and an x-intercept. F of 0 equals 0. F of 1 is negative 27. I'll just let you do that a little bit more slowly. F of 2 is, I believe, negative 16. Again, once again, you would analyze that by plugging it back into the original function. And F of 4, of course, is also 0. We knew that that was going to be, that's an x-intercept, so we knew that value as well. So let's plot f of 1. It's down here at negative 27, so approximately right here. And then f of 2 is at negative 16, which is here. And now, using the information that we have found, let's sketch this graph. We know that from negative infinity to 1, the function is decreasing. So as it has to come through the point 0, 0, we know the function is decreasing until it gets to 1. Furthermore, it is concave up all the way to 2. So as we get to 1, it changes to increasing, and then we know once it gets to 2, it changes concavity. So we know that it must be coming down through the point 0, 0. It's decreasing but concave up until it gets here. Of course, now at 1, it begins to increase, but it's still concave up until it gets to 2. So even though I didn't draw that exactly right, let's put it here instead. And I'll try to erase that little bit that I have. Hopefully it's not too distracting. Everyone makes mistakes. There. And now that we're at 2, we know that something significant happens. It changes concavity to concave down, but it's still increasing until it gets to 4. So what we have to do is realize that even though the function is still increasing, the concavity has changed. So it's concave down now until it gets to 4. Just a slight difference. Notice that this is a cup holding water, that this is a cup that wouldn't hold water, or an upside down cup that wouldn't hold water. Once it gets to 4, what happens? Realize that the function is still increasing all the way to positive infinity now, but we do have another point of inflection here. It's changing back to concave up. So this concave down section now switches back to a concave up section. So here is our sketch based on all of the analysis that we've gathered. Let's take a look at the actual graph. Not bad at all, boys and girls. Look how closely we were able to replicate the actual graph simply by using mathematical analysis. Not a bad day's work, if you ask me. That's it for today's lecture, and I leave you with this beautiful picture. I wish I knew exactly where this was. It's so gorgeous. And this inspiring quote. For since the fabric of the universe is most perfect and the work of a most wise creator, nothing at all takes place in the universe in which some rule of maximum or minimum does not appear. And of course, this quote is by our old friend Leonard Euler. God bless you, boys and girls.